To maximize satisfaction utility, a consumer should allocate their budget such that the marginal utility per rupee spent is equal for all goods. This is known as the equi-marginal principle of utility maximization. Let's break down the information given. Budget B 500 rupees. Price of good X 50 rupees per unit. Price of good Y PY 100 rupees per unit. Marginal utility of good X 200 utils. Marginal utility of good Y MUY 400 utils. Now let's calculate the marginal utility per rupee for each good. For good X, frac MUX PX equals frac 200 text utils RS 50 equals 4 text utils per rupee. For good Y, frac MUY PY equals frac 400 text utils RS 100 equals 4 text utils per rupee. In this specific scenario, we observe that frac MEX PX equals frac MUY PY equals 4 text utils per rupee. This means that the consumer is already getting the same satisfaction per rupee spent on both goods. This implies that any combination of X and Y that fully exhausts the budget will maximize satisfaction given these constant marginal utilities. However, in typical utility maximization problems, marginal utility tends to diminish as more of a good is consumed. Since the problem provides fixed marginal utilities, it suggests that these are the current marginal utilities at some level of consumption, and the consumer should maintain this ratio. To find the specific allocation, we need to consider combinations that fit the budget while maintaining this optimal ratio of marginal utility per rupee. Let's denote the quantity of good X as QX and good Y as QY. The budget equation is East P X times Q X plus P Y times Q underscore Y equals B. 50 Q X plus 100 Q underscore Y equals 500. Since the MUP ratio is equal for both goods, the consumer is indifferent between spending the next rupee on X or Y. This often implies that the consumer can choose any combination on their budget line that allows for this equality. Let's consider some possible combinations, assuming whole units for simplicity. If the consumer buys only good X, 50Q underscore X equals 500 right arrow Q, X equals 10 units. Total utility, estimated for comparison, 10 times 200 equals 2000 utils. If the consumer buys only good Y, 100 Q underscore Y equals 500 right arrow Q underscore Y equals 5 units. Total utility, estimated for comparison, 5 times 400 equals 2000 utils. If the consumer buys sum of both, since frac MEX PX equals frac MUY PY, any combination that fully utilizes the budget will yield the same total utility, assuming these marginal utilities represent the last unit consumed and are constant. For example, if the consumer buys 2 units of Y, cost of Y equals 2 times 100 equals RS 200. Remaining budget equals 500 minus 200 equals RS 300. Quantity of X equals 350ths equals 6 units. Combination X equals 6, Y equals 2. Total utility equals 6 times 200 plus 2 times 400 equals 1200 plus 800 equals 2000 utils. Conclusion. Given the constant marginal utilities provided, where frac MUX PX equals frac MUY PY equals 4 text utils per rupee, the consumer is already allocating their budget optimally in terms of marginal utility per rupee. The consumer can maximize satisfaction by choosing any combination of X and Y that completely exhausts their budget of 500 rupees. All such combinations will yield the same total utility because each rupee spent provides 4 utils of satisfaction. For example, 2 extreme optimal allocations are 1. 10 units of good X and 0 units of good Y. Cost 10 times 50 equals 500. 2. 0 units of good X and 5 units of good Y. Cost 5 times 100 equals 500. And any other combination that fits the budget, such as 6 units of good X and 2 units of good Y. Cost 6 times 50 plus 2 times 100 equals 300 plus 200 equals 500. The problem implies that the consumer is already at a point where the marginal utility per dollar is equal for both goods. Without diminishing marginal utility functions, we cannot pinpoint a single specific quantity of each good, but rather confirm that any budget-exhausting combination provides maximal satisfaction.